Hey Chemistry, Mrs. KJ here, going over 3.11 Inner Transition Metals. The inner transition metals are shown below the main block of the periodic table. So in other words, we're finally going to talk about these down here. In this lesson, you will learn about the inner transition metals. These elements are located in two series or rows that show up at the bottom of the periodic table. Some of these elements are radioactive and some exist only in laboratory settings. The periodic table groups some elements as inner transition metals, some are radioactive, many are made in laboratories, and they're located on the bottom two rows of the periodic table. Goals for this lesson: locate the inner transition metals on the periodic table, give some examples of inner transition metals, discuss some properties of inner transition metals. So you got your study guide. Inner transition metals have a special place on the periodic table. Locate the two rows of elements at the very bottom of the periodic table. These are the inner transition metals. There are two rows of inner transition metals. The first is the lanthanide series. This series starts with the element lanthanum. It includes the elements with atomic numbers 57 through 70. The second row is called the actinide series. It begins with the element actinide, imagine that, and includes elements with atomic numbers 89 through 102. Now, remember we talked about in a different lesson how really they belong right here. It's like we need to cut the periodic table right here, tape these in here, and then tape HF and RF way over here to LU and LR. That's where it belongs. But, of course, the periodic table would have much too long of a shape to fit nicely on a standard piece of paper, and these have special properties, so they throw them on the bottom. The inner transition metals are sometimes referred to as rare earth metals. At first, chemists classified the inner transition metals with the other transition metals. The early chemists soon found that the elements we now classify as inner transition metals did not share the same properties as those other metals. They had their own set of properties. In many text or websites you may browse, you may see the elements of the lanthanide and actinide series referred to as rare earth metals. This is an old term that is deceiving. Some are quite common. Cerium is the 25th most common element on Earth. So when you think about it, 25th is pretty good considering there's over 100. And when they say that it's old, I mean, even when I was going to high school and college, which, yeah, it was the year most of you were born, is when I graduated high school. But still, only, 18 years ago, they still used rare earth metals in a lot of textbooks. Alright, like most metals, inner transition metals are usually found in minerals and mined. In the case of uranium, it is then refined into a powdery cake as seen here. So this is uranium. Inner transition metals have their own physical and chemical properties. Uranium, shown here, is generally combined with oxygen or another nonmetal in an ore. So again, on the bottom of the periodic table. One of the interesting things about the inner transition metals is that these elements are so similar in properties that they are often hard to tell apart from each other. The inner transition metals are typically silver, silvery white, or gray in color. They are very shiny and react very easily with air, resulting in explosions or tarnishing. These metals are very good conductors. The inner transition metals also react very readily with nonmetals. I know, they tell you most of them are silver and then they go ahead and show a white one. Elements not found in nature. Elements 93 to 102 do not exist in nature. These are what are called trans-uranium elements. Trans as in beyond. So they're beyond uranium, which is number 92. So zoom in a little bit here. So we have uranium down here. So starting with neptunium and then going this way, these are man-made. They're beyond uranium, so they're called trans-uranium. Scientists produce these elements in laboratories using nuclear equipment and particle accelerators. The trans-uranium elements are radioactive and decay rapidly, and thus do not exist naturally on Earth. The most well-known of these elements is plutonium. If you're thinking, I've never heard of that, plutonium has a lot to do with atomic bombs. Samarium is an element in the lanthanide series. The lanthanides are soft, silver-colored metals. They are reactive, will tarnish quickly when exposed to the air, and will even react with water if given enough time. Samarium, Sm, has an atomic number of 62. Samarium, like other metals of the lanthanide series, has commercial applications. So again, we're talking about the lanthanide series, or that row right there. Samarium is used in nuclear reactors and in lasers. When combined with cobalt, it makes very strong magnets. And a radioactive isotope of samarium, samarium-153, is used in medicines to treat the severe pain bone cancer patients may experience. Many of the intertransition metals have extreme applications. Samarium is used in high-powered magnets and in lasers. Europium is another lanthanide series intertransition metal. Europium, Eu, is an intertransition metal with the atomic number 63. It was discovered in the 1890s and named after Europe. Europium is the most reactive of all the intertransition metals. It reacts with water quickly. Europium is also very ductile. Europium has few applications. Some forms of europium are used in electronics, such as televisions. It can be used in procedures to test for Down syndromes and other conditions during prenatal exams. Europium, like the other intertransition metals, is not found as a pure element in nature. It is found in minerals such as monazite. Europium is rarely found uncombined with other elements. This is a photo of wow, I can't say the word, can I? Monazite, a common mineral containing europium. All elements of the actinide series are radioactive. Okay, so we're bouncing back to the actinide series. Out of the 14 elements in the actinide series, only thorium and uranium occur in nature in any significant quantity. Actinium and proactinium are found only in trace amounts, so that means little tiny amounts. The majority of the elements in the actinide series are trans-uranium elements. Recall that this means they are only produced in the laboratory. So trans, beyond, they have atomic numbers higher than uranium's, which is 92. Actinide series elements have nuclei that are so large that they tend to break down. All actinide elements experience natural radioactive decay. Radioactive, emitting radiation in the form of particles or electromagnetic waves from the nucleus of an atom. So either the particles or electromagnetic waves. Electromagnetic waves can be gamma rays, microwaves, infrared rays, light, the different colors, radio waves, stuff like that. It's coming out of the nucleus of the atom. Actinides. Even though some of the actinides are short-lived and created in labs, an element like plutonium has a great value in the nuclear energy industry. So, kind of zoomed in there. Uranium is a well-known element in the actinide series. Uranium, U, is an intertransition metal with the atomic number 92. Uranium is found in nature in the form of 3 different isotopes: uranium-238, uranium-235, and uranium-234. So isotopes means that they have more or less what? Neutrons, and that makes them heavier or lighter based on how many neutrons they have. Uranium is found in the water, soil, and rocks on Earth. It does not exist by itself, but is found in minerals such as uraninite, lignite, and monazite, and in phosphate deposits. Uranium is radioactive and decays naturally. Many hypothesize that the radioactive decay of uranium, with the release of particles or energy, is one of the sources of heat in Earth's interior. This heat is needed to keep the outer core in the liquid state and drives the convection currents in the mantle. Uranium has been used for nearly 2,000 years as additives to ceramics. Uranium is mined on almost every continent. This mine is in Australia. Once mined, uranium is purified. After purified, it appears as a powdery cake. Einsteinium. Einsteinium is a synthetic intertransition metal named after Albert Einstein. Einsteinium has the atomic number of 99. It was discovered in 1952 at the University of California at Berkeley. A scientist was studying debris from a nuclear reactor and found an isotope of einsteinium. The discovery of the element was kept a secret for several years because of the Cold War. To make einsteinium, because it does not occur in nature, because it's above number 92 in our actinide series. So what do we call that again? It's beyond uranium. It's trans uranium. Okay. To make einsteinium, because it does not occur in nature, scientists start with a sample of plutonium. The plutonium is placed in a nuclear reactor. This results in the formation of a different isotope of plutonium, which is then mixed with aluminum and made into small pellets. The pellets are placed in 2 more reactors for over a year. The result is a mixture of californium, another actinide metal, and einsteinium. Plutonium is the starting point in making einsteinium. This photo is a sample of molten plutonium ready for use. The intertransition metals are unique elements. The intertransition metals are composed of 2 series of elements, the lanthanide series and the actinide series. While these elements are, for the most part, not that significant commercially, they do exhibit properties of elements that are unique and interesting. Many of the intertransition metals do not exist naturally and are only produced in the laboratory. Periodic table groups some of the elements as intertransition metals. Some are radioactive. Many are made in laboratory. They're located on the bottom 2 rows of the periodic table. All right, let's get some notes down. I kept the first paragraph and the goals. Keywords and pronunciation. Emitting radiation in the form of particles or electromagnetic waves from the nucleus of an atom. So that's what radioactive means. Transuranium. The chemical elements with atomic numbers greater than 92. Why? Because uranium is number 92, and these are beyond or trans uranium. Alright, so then I added to our notes intertransition metals, the lanthanide and actinide series. They are below the periodic table, although really they fit in the middle of the periodic table. And so this is what I mean by that. So this is how we have the periodic table look, but really the lanthanide and actinide series belong right there. So that's why I made these 2 boxes, which are empty, that same color, to show you that, oh yeah, really they squeeze in there, but we put them below. The intertransition metals are very reactive. Many are radioactive, which means they are also unstable, and many are man-made as well. All right, so again, I want to go over these keywords again. Radioactive, emitting radiation. So stuff's coming out of the nucleus. It's in the form of particles or electromagnetic waves, like infrared rays, gamma rays, X-rays. Okay, and it's coming from the nucleus of the atom because there's so many neutrons and the nucleus is so huge. That's why this happens. That's why they decay into other stuff. And other stuff, I mean other elements. We also have transuranium, the chemical elements with atomic numbers greater than 92, because uranium is 92, and these are bigger or beyond uranium, and they're man-made. Okay, that's it for this. Good luck on your quiz.